Hello students, in the last class we have discussed electromagnetic induction, induced EMF, Faraday's experiment, Faraday's laws, isn't it? And towards the end of the class we have derived E is equal to minus n d phi by dt. Why this minus sign is written before it? That will be explained by Lenz Law, and I will explain that. Before that, let me tell you more few things. Here you see, suppose this is the coil having n number of turns. This capital N represents number of turns in the coil, and d phi by dt is the rate of change of magnetic flux, through this coil. Suppose R be the resistance of this coil. Then EMF induced is E here. So according to Ohm's law, I is equal to V by R, right? V means potential difference, and I have already explained in the first class that electromotive force, that is E, is nothing but it is potential difference, E by R. So we can write I is equal to E by R. And current, we know that current is also nothing but rate of flow of charge. So here, as E is induced, EMF is induced, so there must be a current flow. Current must be flowing in this circuit, in this loop. So that current, suppose dq charge, current is, I have already told you that current is rate of flow of charge. dq charge flows in dt time, then I is equal to dq by dt. If dq charge flows in dt time, then current I is given by dq by dt. So I is equal to dq by dt. So in this case, dq is induced charge due to induced EMF. So from these two equations, what we can say? We can say these two are also equal because the left hand sides are equal. So we can write E by R. E by R is equal to dq by dt. So now you see, E is minus n d phi by dt. Now let us replace this E by this value of E. So then we will get minus n by R d phi by dt is equal to dq by dt Now removing dt from both sides, we will get n d phi by R is equal to dq, right? Or we can write dq is equal to minus n by R d phi. That's what we can write. So this is induced charge. So hope you have understood. This is the expression for induced charge. Now here you see. So let me explain with the help of Lenz law why this minus sign is written here. So now what is the Lenz law? So let me clean this first. Here you see, Lenz law states that Lenz law states that the induced EMF, in a coil oppose the change of magnetic flux through the coil. So this is the Lenz law. So here you see this induced EMF. So when magnetic field is changed, when magnetic field is being changed continuously through a coil, EMF is induced, and this induced EMF again oppose the change in magnetic flux. So that means when you bring this magnet towards the coil, this coil will oppose the magnet to coming towards it. That means to oppose the north pole, here if it is north pole, then to oppose this north pole, this face will appear to be north. And when you will move away from the, this is the coil, when this north pole is moved away from the coil, then it will try to attract this magnet towards itself, towards it. Then to attract this north, it should be appeared as south. So that is the phenomenon goes here, goes on. Then here you see this happens to oppose this rate of oppose this change in magnetic flux, isn't it? And rate of change of magnetic flux is given by d phi by dt. So that's why E is equal to, there should be a minus sign, minus d phi by dt. If there are n number of coil, n number of turns, then there should be n. So that's why this minus sign is written, because this EMF oppose the region for which it is induced in this coil. So region is change of magnetic flux, and this EMF oppose this change in magnetic flux. That's why this minus sign written here. So hope you have understood this. Now here you see, let me explain few more things. Suppose you have a coil. This is a coil, suppose circular coil. Now let us suppose the current flows through this coil. Current in this coil is suppose in the direction anti-clockwise, in anti-clockwise direction, anti-clockwise. It is anti-clockwise. Then here you see what will be the direction of the magnetic field due to this current. That will be determined by this right hand thumb rule. So if you work the consider that if you work these fingers other than the thumb, the remaining fingers are work in the direction of current in this loop, then the thumb point outwards, isn't it? Normally outwards, in this way, normally outwards. So let me represent the outward direction by dot. So it is normally outward. So then, so here you see, we know if you take a bar magnet, this is the north pole, this is the south pole. We know that magnetic field lines outside the magnet emerge from north pole and merge at south pole. So as in this case, according to right hand thumb rule, the magnetic field line is coming outward. So in magnet, outside the magnet, emerge from north. So it is coming outward in this case, according to right hand thumb rule. So that's why this face is this face behaves like north pole, and this is the coil. If current flows in opposite direction, in the direction clockwise, suppose in this way, it is now flowing in electric current flows in clockwise direction. In this case, clockwise. clockwise direction. Then what will happen? Now work the fingers in this way and stretch the thumb. Thumb is pointing into the board, and to represent the direction into the board, let me use cross. This represents out of the board, and this represents into the board, that means it is going in. So this magnetic field lines emerge from north and merge at south. So this face of this lobe will behave like south pole. Is that clear? Hope it is clear to you. So now let us discuss about Fleming's right-hand rule. Fleming's right-hand rule. Fleming's right-hand rule. Suppose, let me consider, this is a magnetic field. These are magnetic field lines, and I am writing cross. That means the lines are pointed into the boards, perpendicularly into the boards. They are entering in the board perpendicularly, normally in this direction, like this. Okay, that is represented by cross. Now, suppose this is a conductor. This is a conductor, and it is moved in this direction. So what we are discussing? Fleming's right-hand rule. So this is the conductor, and it is moving in this direction. This is the direction of motion of the conductor. Motion of the conductor. And this cross represents the magnetic field, direction of magnetic field. So what is the direction? Into the board. Normally into the board. That means perpendicularly into the board. So then what will happen? So this is the direction of magnetic field into the board, and conductor is being moved in this way. So when it will cross the magnetic lines of force, there must be a induced EMF due to the change in magnetic flux through this. So due to the change in magnetic flux across this, so what will be the direction of EMF in this conductor? So that will be determined by Fleming's right-hand rule. Now let me tell you how. Now take your right hand and stretch the three angles. Spread these three angles mutually perpendicular. Thumb, first finger, and the middle finger. So if the thumb pointed towards the motion of the conductor, this conductor is being moved in this direction. This is the motion. So this is the thumb. Thumb is in this direction, and the first finger should be, this finger should be pointed towards the magnetic field, that is into the board. Then this finger, this middle finger, will point towards the induced EMF. So in this case, it is downward. It is downward. This finger is pointing downward, while the first finger, this finger is pointing into the board, and the thumb, this thumb is along the motion of the conductor in this direction. So that's why. So EMF, this is the direction of EMF. So here you see, let me show you. This is the direction of the motion, and this is represented by the thumb. And into the board, this is the into the board. This is the direction of magnetic field. This is pointed by first finger. Then direction of EMF is represented by the middle finger of the right hand, of your right hand. This is the first finger into the board. This is the thumb in the direction of motion of the conductor, and this is the middle finger. It is pointing downward, so direction of EMF is downward. So hope you have understood. This is the Fleming rule to determine the direction of EMF induced in a conductor or in a circuit while magnetic flux is being changed across it. So hope you have understood. In the next video we will discuss about motional EMF. So in the next class.